So we are here in this nice campus of the University Polytechnic of Madrid to perform the final demonstration of the project, to perform the field trials. So this project is a project that involves partners from 3 different countries, from Portugal, Spain, and France. So from Portugal, we have the Institute of Telecommunications and a SME, a company of Omics that deals with the genomic data, that in this project enter kind of like an end user of the results of the project. From Spain, we have the ICFO from Barcelona, and the University Polytechnic of Madrid from here, from Madrid. And from France, we have University of Sorbonne and the INRIA. So all these groups, all these researchers have been working, trying to develop services, and in this case, our service is related with the use of very critical data, in this case, genomic data. So the idea is that we can profit from the use of the data, but making sure that we preserve the privacy of the patients. So we are using secure computation techniques. So we are using secure multi-party computation techniques based on cryptographic keys generated using quantum technology. So in terms of quantum technologies, we have three types of systems. So we have continuous variable systems, entangled based, and discrete variable systems, and we also run 3 different applications in terms of services that we can provide to this client, this Omics client, that in this case defines both the problem and also the services that we are providing.
So here I switch from the RBF to the linear to be faster. And what we're going to see, basically, first is the Z-score. So the anomaly detection in about 60 seconds. The orchestrator will go to all of the computation nodes and ask for information of whether they have inputs to add to this computation. They will say that they have, so it will instantiate the computation. Here are the logs. This is red because there's no trees, and then hopefully we'll start seeing here in the logbook the computations and start filling basically the values. Or we can have data here. Actually, we can add data directly as seems that they have it right now. That is to add the data directly to this interface, or in batch using a CSV file. So we are executing now the Z-score computation. Let's see if everything is going well. This one takes, since it's between the 3, it takes usually about 30 to 40 seconds. It has finished. You see here some of the data that's around 30 seconds. Took 30.71 seconds. So now if we go to the laboratory test that we went here before, now we have the Z-score. For each of the variables, we have the Z-score. In here I'm putting in red everything that is above 1.5 or below 1.5. But still, we don't know if this can accept the transplant or not. One small detail, for example, is that actually the first, for example, the first test is exactly the same as the first one that is here. And we'll see that even though they were performed on opposite sides, the values are exactly the same.
And we have some different ideas to test, also with the Spanish Meteorological Center that has a Celsius log, and we want to use a frame of calcium. And it's Alberto is the one doing more or less this section. We have there other section with that you use to do some proofs and to have the devices there and being able to connect quickly. But the main room is this one, that is the rack room. We can enter more or less, but it's full of cables now because all the all the setups, like Adriano setup, has grown a lot. If you remember, all the network, this is like the one that is usually in the bottom, and in the pre-linked scenario, this in the CCS is the one that is far apart. So here we have a lot of the different vendors, and we are doing some tests, and other things are more or less configured for production. We have there the SMSPD from IDQ, that is the one that Adriano is using for his protocol.
So we have a ring here in the campus.
This ring has been used to test, do some tests. So Adriano was using it to go around and going back here. So
and the other node that have been used is this one.
Is Rectorado.
I came to the UPM to implement my protocol based on entanglement. So basically, I am building a setup that it's building a new quantum oblivious transfer implementation that basically uses entanglement as a source to deliberate this information in a quantum oblivious manner. Right now we are in the center of Madrid. We are in the exit node, and basically my experiment is deployed between this node and Rectorado. There is a few kilometers away from here. My experiment, entanglement based, is one with the shortest distance. The good thing with collaborating in such an international environment is that you get to know people that have different backgrounds, so then you can learn from them, and also you can show and exchange ideas, and it's something super fruitful for the experiment because we get to understand better the part of the deployment. I am more based in the lab, working in the optics and the post-processing, but I'm not that related to the network layer, so then getting to work with the people from the UPN, it's really nice. The great thing about these projects is that it enhances the collaboration, and it gives a framework so that we can collaborate between the different institutions. So it's easier to have some mobility and get to know the other laboratories and basically gain more experience and knowledge from other places, and to have a common framework, it's always something that it's great.
So far, the experience with the QuantaGenomics project has been wonderful because we had the opportunity to collaborate with a wonderful set of teams in different countries, and I think we've progressed a lot in the development of our devices and technologies. What we did in our team at ICFO was to put into practice an entanglement-based protocol with practical devices. So we had to modify the protocol to make it feasible with experimental tools in order to make an experiment that is useful in practice and scalable in the future. So we've taken this theoretical protocol and we adapted it to practical terms. So the best part of working in this collaborative project was to enable to interact with people who have different backgrounds and have different approach to the technology. So for instance, we had the opportunity of collaborating with people who do things more related to the application, like the final users of the project, and also people who develop basic technology that can be used to other platforms as well. The most gratifying experience of working in QuantaGenomics was to perform this final deployment in Madrid, because we could work with different teams and push our technology to a practical case where we have to not only being able to operate things in the lab, but also outside the lab with the challenges that it implies. So for us, it was a very particular moment. It was very nice, very challenging, of course, but it's also very gratifying.
So basically now we have the control station, which is this device here that is controlling remotely the preparation on L side, and is receiving the data here, checking the quantum bit error rate on each channel and plotting it, so we can run it actually. So if I acquire a set of 200,000 states, we can see that it's preparing and sending the states, and we have a total Q-bar for this set of acquisition. So we receive the 67,000 states out of the 200 that I sent, because in this moment the mean for a number is quite high. So it's like 33%. And the quantum error rate in total is 1.2% for this acquisition, and each basis number is detailed here. So we have actually the first channel and the third one that is below 1%, and the other two that are a bit higher. So we have 1.2% for the second channel and 2.1% for the fourth channel. So the idea is that this runs continually, and then once the total batch of data that is required, so the post-processing to execute is acquired, the post-processing is launched, then this is the keys for the KMS.
At the same time, I see on the wavelength division multiplexing a reference signal that is generated, that is blocked in the same reference that drives the sampling of the DAC and drives all the logic inside the FPGA, so that reference was passed in the final on a different wavelength in 1,300 and again nanometers wavelength. So it's in parallel with the quantum signal with the fiber, and we send that to synchronize the physical layer of the transmitter in the physical layer of the receiver. Basically, this is the signal in which my DAC and ABC of the transmitter must be locked. It must lock to this reference. So the first phase of the bootstrap is that ensure that I get the PLLs locked. The PLLs that generate that's a bit locked for the DAC and the transmitter. And here you see the receiver is locked to that reference. And if it's locked, I have the physical around.
Where we are having the last mile, so to speak, in which we are putting together all the different devices from ICFO, from Sorbonne, and from Aveiro, and they are putting together here in the network that we have, where we have the final demonstration for multi-party quantum computation. The infrastructure that we have here is one of the largest quantum networks here in Europe. We have over 700 kilometers of fibers. But anyway, the point here, what we are using is 3 different sites, and in which we have the different devices installed, and then they are passing this beyond QPG protocols, because they are using of these keys actually to do this multi-party quantum computing, which is something that goes beyond what is the usual use of quantum communication right now. It's used most of the time quantum key distribution. Obviously, with quantum communication, you can do many more things, and this is one of the things that you can do.